Right, welcome back. So by now you should luckily know all the basic gates and also you should know about flip-flops and so on and so forth and latches and so on. But what I want to talk about today is the difference between the real world and something that we have been dealing with, which is our idealized world. And I'm going to talk about the buffer. So we're going to talk about the one new gate, which is fairly simple. It's just, the one of the most, one of the easiest gates that you can draw and deal with because, it just, essentially, you can think about it like as if it does nothing in an idealized world. But it's very important in the real world, and you're gonna see why. So, among our logic gates, what we know that this one is an AND gate, that this one whoops, we go, is an AND gate. This one here, again, is an OR gate. This one here is a NOR gate. This one here is the exclusive OR or XOR gate, which is essentially like the OR gate, but when both the input are 1, then it's not gonna output 1. This one instead is the exclusive NOR gate, so XNOR gate. And then we can also have the buffer gate and our old friend, the NOT gate. So this is a NOT gate and it is the buffer gate. So we have been using all those gates pretty extensively, to be fair, within those lectures. Because the AND gate, so 1 and the other have to be 1. The NAND gate is the same but with a NOT, so everything is inverted. The OR gate, at least one of them has to be 1. If they're both 1, then it's fine. NOR is the same but inverted. XOR, exclusive OR, so at least one of them has to be 1. But if both of them are 1, then it's not going to be valid. Exclusive NOR, it's like the same but with a NOT. Buffer, well, we have been using the NOT gate. We basically said, okay, if I get like 1 here and I put it through the NOT gate, I get 0 here. And if I have 0 here, go through the NOT gate and I get 1 here. So that's as simple as that. But what does a buffer do? Well, if I put 1 through the buffer, it outputs 1. If I put 0, it outputs 0. It outputs 0. So why is it useful? Well, for two reasons mainly. The very first reason is that, well, as you may know, every single gate introduces a delay. So whenever you go through one of these, you're gonna have introduce a delay, but it's not the reason why it's useful. It's more like a feature, well, perhaps an unwanted feature, but anyway. But the reason why it's useful is that, let's assume that you have a circuit, right? So perhaps you have, I don't know, like an AND gate here, okay? And then you have down the line, very far away, a series of circuit. Well, the same circuit, but with a series of elements, which take this data as an input, and I don't know, some other data in here, and you have like, I don't know, another AND gate, and then it goes down and you have something else like an OR gate, and which takes the, so we need to put from something else, and then you have a bunch of other stuff like, I don't know, like this one and this one here. I don't know, other things like from here you get, from another place you get something else, like another AND gate and this other AND gate, which takes this from something else as well, right? So let's suppose that you have this kind of circuit. So we have an AND gate, an AND gate, an OR gate, an AND gate, and an AND gate. The problem with this circuit is that the output of this one, which is going to output something, it's going to be very, very far away from this one. So basically it has to travel a very, very, very long distance before it goes to this other AND gate. And sure, we are, you know, drawing those things with a pen and paper, or you may do that on your computer, on a software, is fine. It doesn't really matter. But the important thing is that even though we are in digital electronics, when we think about a signal, we think about something that goes between 0 and 1, right? Because, you know, we are in Boolean algebra. So let's suppose that we have, I don't know, like we have 1 and 1, and the output is 1 here. Okay, so what does 1 means? Well, it means that the voltage is high. So how do we represent this? Well, if you think, let's suppose that we get a series of inputs here, okay, and this one is low voltage and this one is high voltage. So whenever we draw it, we generally draw it like this. So I suppose that both were 0, then we switch to 1, 1, and we stayed, and we switch to 1, 0, so we go down, and we stay 1, 0, then we switch to 1, 1 again, then we switch to 0, 1, and we go low, and then we switch to 1, 1 again, and we then switch to 0, 0 back, and we stay low. Okay, let's suppose that we have something like this in input. In real life, what you are actually going to get would be something like this. So you have 0 and 1, but you're not going to get something like this, because in real life, this is the voltage, but the wire itself has some kind of resistance, and it has to travel through here. We have high voltage, sure, but how many amps are we drawing from this? It's just to travel through all the way down to here. Yeah, it's not like this perfect, like 0 and 1. We may have something like this. Instead of this, we may have something like this. So then it goes down, and it goes up again, and it goes down, and it goes up again, then it stays down. Now, this is what happens if we read it like here. okay? We read it here, and we get something like this. What happens if we read it here? So what this AND gate actually is saying is not definitely not this, but it's not even this. It's something like this. It's more like something like this, 0 and 1. So this one is actually saying this. So it goes up, but just a bit, then it goes down, just up. It goes down, just up, and then it goes down. Now, the problem with this is that we actually expected our high voltage to be here. But it's never going to reach that because, you know, it has to travel all the way down here. So, you know, what do we do? Well, what we do in real life is basically saying, okay, if it's above, like this threshold, I'm gonna consider it as 1, so high voltage. If it's below this threshold, then I'm gonna consider it as a 0, as a low voltage. But that's a poor approach anyway. So what will we do? Well, we use a buffer. So if I put a buffer here, and I say, okay, let me just put a buffer here, and perhaps a buffer here, and perhaps a buffer here, and perhaps a buffer here. So now I have those buffers. So what do they do? Well, this buffer is actually getting, you know, this crap, okay, this crappy wave, and so saying, okay, it's actually above the threshold, so I know that it has to be 1. It cannot be, in Boolean algebra, it doesn't make sense to have a value which is between 0 and 1 as a voltage, so I know that it has to be expressed as 1. So, for instance, if in our circuit the high voltage is 5 volts DC, and I see it above like 3, and our threshold is like 3.3 volts, and there has been a huge drop in voltage, then I'm gonna say, okay, I'm gonna push it up and make it 5 volt, because for me it's a 1. So what happens is that it takes this crap as an input, and as an output it gives us this. So yeah, it goes all the way to 1 again, and then it goes down, and then it goes all the way to 1 again, and then it goes down, and then it goes all the way to 1 again, and then it goes down. So this one again is not our ideal ideal step from 0 to 1 and 1 to 0, 0 to 1, 1 to 0, and so on, but it's really damn close to it. And it's definitely way better, because when we analyze 1 and we expect the 1 to be here, well, it's actually here. So this way it has to travel just a little bit to get to this AND gate here, and then another little bit to get to this OR here, and another little bit to get to this AND here, and another little bit to get to this AND here. It doesn't have to do, you know, to travel all the way to here without any buffer, because otherwise the signal was going to be degraded. With potentially unexpected things, like, for instance, let's suppose that it was going to go, you know, below this threshold, which was, I don't know, 3.3 volts, and this one was, say, 5 volts, okay? Let's suppose that it was going to be below, like, 3.2 volts, which doesn't make sense, but then it would have been, you know, considered by this AND gate as a 0. That's bad. That's like, no, that's not what it's supposed to happen. So yeah, this is basically why we use the buffer. So a buffer is actually very, very important, because it takes something in input and it outputs the same thing, but at the very right level. So you may be tempted to consider it as an amplifier, but it's not really an amplifier. It's not really an amplifier. It's just, it has a certain threshold, and it basically trying to recreate what it's supposed to recreate in a best possible way. So we start with, well, not this, but this. And even if it's degraded, the buffer tries to get this one back. So it tries to recreate this. So yeah, this is one of the advantages of having a digital circuit, because you have, for instance, you have 0 and 1, 5 volt. You consider it to be 1, so everything is 1. Having something in between doesn't really make sense. So if there is a drop, something is wrong, something is not right. So yeah, this is basically why we use a buffer. So again, when they ask you about the gates, please remember that there are not just those, which are the classic ones, but also the buffer and the NOT. So AND gate, NAND gate, OR gate, NOR gate, XOR gate, XNOR gate, buffer, and NOT gate. Right? Bye for now.